Okay, let's talk about energy levels. Now, this is all about where those colors come from when you heat up, let's say, I don't know, lithium chloride. It gives off that nice red color. Well, why is it red as opposed to sodium chloride that gives off a nice orangey yellow sort of color? So the sort of traditional flame colors that you get. Well, it's down to what the electrons are up to and down to a bit about how electrons behave. So let's just have a look at an atom. So this is my really bad drawing of an atom. There's the nucleus of the atom, and what we've got around this atom are these things called electrons. Now, electrons in the GCSE sort of model are particles with a negative charge, very little mass, and they orbit the nucleus. Well, the reality is a little bit different from that. And in reality, what you've got is electrons certainly going around the nucleus, but they don't just exist as points going round in circles like planets. They exist as regions of negative charge, places where you could potentially find an electron. And those electrons can have differing amounts of energy. And there's this idea called an energy level. Now, this may look like a traditional drawing of an atom. So we've got a circle there, and I'm going to draw a circle around here, and I'm going to draw a circle here. Now, I'm going to try and make this line a little bit closer than I made the other one, and I'm going to do one more. You see, I'm drawing this with my finger, so it's not brilliant, but perhaps you get the idea that these lines are getting closer together. And I'm going to have, there you go, a little electron there. Now that's what we call a ground state, okay? And a ground state is the minimum amount of energy that electron can have when it's associated with that atom. So what happens if you stick a Bunsen burner up this thing is that that electron can transition to a higher energy level. Basically, it gains some energy, but it can't just gain any old amount of energy. It gains a very specific amount of energy. And they're defined by these energy levels. Okay, so I've only drawn 3 more energy levels, so they would be the amounts of energy that electron can gain. It can't gain half that amount or 3/4 of that. It can only gain that amount of energy. And that's what we call energy being quantized. So let me just shrink this down and put it over there, and just write that word because it's very important. Quantized. So energy is in little packets. So if you like, this is packets of energy. Okay. So what happens now that those electrons are excited? Well, what happens is that they just go back to this for a second. What happens is that they lose that energy over a period of time, and they fall back down to a lower energy level. So I do that in a different color. So if that electron had gone up to the first energy level there, it could lose some energy. If it went up to that energy level, it could lose a little bit more. And if it went up to that one, it could lose even more. Okay, it ends up where it started, but depending on how much energy it gained in the first place, it gains more and more energy. So each time it does that, it gives off a photon of electromagnetic radiation. In the case of what we're looking at, that's visible light, and that's defined by the equation E. That's the energy gap that we've got there, the amount of energy that photon's getting, multiplied by h, which is Planck's constant, times by the frequency of the radiation. So what we get are three distinct colors here. Just rotate that a bit and put it into there. So that gives us something called a spectrum. So we're literally getting three different specific colors coming out of there. So if you imagine we've got, let's go white, we're looking here, and these bigger lines, the ones going from a higher energy level to a lower energy level, they're giving, that's a higher energy transition, so that's light with a higher frequency, so we've got more energy associated with it. So this is going to give us slightly bluer light, it's higher energy, and we'll get three lines because we've got three transitions there. Okay, and that is increasing frequency and increasing energy. Okay, so if you were looking at this through a little spectrometer, so just a little single slit spectrometer, what you'd be able to see is literally these lines, these colors, and these colors here are very specific to a particular element. However, if we go back to this for a second, I'll zoom in a bit, something else can happen. Now I do this in red. An electron might just go down to this energy level, or it might go down to just that energy level. Now you notice that they are smaller gaps than the blue ones. Okay, so that means it's lower energy and therefore lower frequency, and that gives us a new set of lines. Just shrink that back down again and do a little bit of penning. So that'll give us another set of lines here, and these lines are now lower frequency. If I go back to this diagram again, now I've only done a few energy levels here, but in reality there are actually a lot more. Do this one in white. So I could do that transition as well. Now that's the smallest energy gap of all. That's the lowest frequency. So we go back to our diagram. That would give us a line. That would give us a line round about there. Okay. So for a given element, we're getting a series of lines being produced because electrons get excited to higher energy levels and they can only fall back down to energy levels which are lower than that, and there are combinations, as you can see, of energy levels they can fall back to. They can fall back to what's called the ground state. So I'll put that word in, that's important. It's the ground state. Put that over here. And the ground state is that energy level there. Okay, so that's the minimum amount of energy an electron can have. But there's these amounts above it, and they can go up to that, and they can fall back. And this is how we get this spectrum of lines. And these here are specific to an element. Okay, so this series of lines will look different depending on what element you got there. So you can use it as a method of identification of elements by looking at where these lines are, how much energy each of those transitions, and what the frequency of each one of those transitions is, using the equation oops, let's go back to there. Using E equals h mu, so energy equals Planck's constant times the frequency. So you can measure the frequency, you can work out how big these energy gaps are, and you get some understanding of the electronic structure of an atom. And this is how we've come to this understanding of the fact that there are different energy levels of electrons in atoms, because we can look at these spectra and we can actually piece together where all these energy levels are. This is something that we'll look at in the first few lessons of AS chemistry. So some of you will have looked at this already to an extent. Some of you will be doing this week. Okay, hopefully that was sort of useful.